Again, let's return to the fly experiment that we've been discussing. So if the gene for white eyes is one gene with two alleles on an autosome, right, inherited by the usual Mendelian rules, then each progeny should have a 0.5 probability of being white. And it should have a 0.5 probability of having red eyes. Right, a 50-50 chance one way or the other. But instead, what we've observed is out of 5 flies, 4 of them have red eyes, and 1 of them has white eyes. Did we just get unlucky, right? Or is there enough evidence to suggest that these kind of usual Mendelian rules are actually don't apply here, that they're being broken somehow? We call each of these possibilities, these possible scenarios, a hypothesis. So formally, let's call the first a null hypothesis and the second an alternate hypothesis. So we write the null hypothesis H0. And the null hypothesis is the default, right? This is the one that we assume is possibly or probably true. And in this case, the null hypothesis in this experiment is that the probability of seeing a fly with white eyes is 0.5. Then the alternate hypothesis is that this null hypothesis is false, right? That there's something else going on here. We'll write this HA. I think your book calls it H1. This is the alternate hypothesis. And in this case, we'll say that the alternate hypothesis is that the probability that the flies have white eyes is not 0.5. Right? We don't have to set a particular probability. The alternate here is just that the null hypothesis is false. If the null hypothesis is that the probability is 0.5, then here anything else, right? Anything else that we have enough evidence for is the alternate hypothesis. And we saw in the last video that under the null hypothesis, the probability of seeing 4 red-eyed flies and 1 white-eyed fly is 0.15. We'll say the probability of 4 red-eyed flies and 1 white-eyed fly given the null hypothesis is approximately 0.15. But is this enough? Is this strong enough evidence that we should reject the null hypothesis in favor of the alternate hypothesis? Let's actually reframe that question just a little bit. Let's say that if we performed the same experiment, right, we looked at 5 flies a whole bunch of times, right, hundreds or thousands of times, and the null hypothesis was true, how often would we see an outcome that was at least this extreme? Let's say that we're going to reject the null hypothesis if we see an outcome that's at least this extreme, only 5% of the time or less. And we'll call this 5% the critical value. 0.05. Right, so if we ran this experiment over and over and over and over again, we will decide up front that we're going to reject the null hypothesis if we see something this weird at least 5% of the time. So answering this kind of question, right, is there enough evidence to reject the null hypothesis in favor of an alternate, is called hypothesis testing. And this is a super broad field of statistics. Fortunately, there's a very widely used method in genetics that we can reach for called the chi-square method. It's used to see if a set of observations, like we've been looking at over here, matches a particular ratio. There's chi-squared method. So let me go ahead and walk you through how this works. First, we predict the observations that we would see if the null hypothesis were true. And so in this case, observing five flies, we would expect to see 2.5 of them to have red eyes and 2.5 of them to have white eyes. And yes, in this particular instance, a decimal is okay, right? The fractional number is fine. And then we compute this chi-square value called the chi-square statistic, and that is chi-square is the sum for each class of observed Let me go ahead and write this out in the middle. Here we go. So chi-square is the sum over all of the classes of observed minus expected squared over expected. And again, this uppercase sigma, this Greek character, means the sum. And so the sum over all of the classes means we're going to do this once for flies with red eyes. We're going to do it again for flies with white eyes. We're going to add those together. And so in this case, we've got 2.5 minus 4 squared over 2.5 plus 2.5 minus 1 squared over 2.5. And the chi-squared statistic, our final value here is 1.8. What does 1.8 mean? Well, we actually need to take this value and look it up in a chi-squared table. And there's one of those in your textbook. You can also find them all over the place online if you type in chi-square table into Google. However, before we can find a useful an interpretation for this value, we need one more thing, which is called the degrees of freedom of the experiment. And in this case, the degrees of freedom is the number of classes minus 1. And so in this particular instance, we had two classes, right? Red eyes or white eyes. And so the degrees of freedom are 1. And we find that when we look up on the chi-square table, this critical value of 0.05, remember, we're going to reject our null hypothesis if, when we do this a whole bunch of times, we find a value that is at least this extreme 5% of the time. Well, this chi-square number can be represented as, like, how extreme is this observation, right? And so we'll take our critical value, we'll take our number of degrees of freedom, and we find that for a critical value of 0.05 and the number of degrees of freedom of 1, we need to see a chi-square, like the cutoff from the table is 3.84, right? And again, I didn't come up with this out of my brain. I looked it up in a table. And we say that if our calculated chi-square statistic is greater than this number, then we can reject this null hypothesis, right? We compare the number we computed with our data to the cutoff value that we found in the table, and if this number is bigger than this number, we reject the null hypothesis in favor of the alternate one. And so in this case, we fail to reject it, right? We say that this result is not significant at a p-value of 0.05. And in other words, it just seems like we got unlucky here. This chi-square test is really broadly useful. It is something we are going to see over and over again this semester. Whenever the question is, I expect this set of proportions, I saw this set of proportions, is that deviation significant?